Okay, so now recording it, but we're in section 1.3, word problems. So basically, life's a word problem. Work it out, right? We're going to have, you know, lots of situations that we have to deal with throughout our life that we have a lot of unknowns and constraints and limitations. So there's mathematical ways we can go about, solving a lot of these things. So what we want to do is we want to utilize math models. In a course called Finite Math, I look at math modeling. Actually took a course called Math Modeling, but what are math models? Math models are composed of two things. They're composed of factors and constraints. So factors plus constraints. And then what does that mean? Uh, Factors are the unknowns. So usually we label variables, right, in the math world. Unknowns. What don't you know that you want to know? If I don't know what the length of a rectangle is, I can call it L. But if I don't really care what the color of a car is, I don't need to label it. So we're gonna labeling variables is what we're gonna do for factors. So that's kind of what you're used to in the math side of uh, what factors are. So only label what you don't know that you want to know. So if we're not interested in really knowing what it is, we don't have to worry about, creating a variable for it. A lot of times we can look at the question that's being asked, and if it says, hey, what's the length of a rectangle, then we can say, let L equal the length type deal. And then what are constraints? Constraints are limitations on what can be accomplished. Limitations, they could also be restrictions. So in other words, we might only have 100 yards of lumber, something like that. So we could be restricted there. Okay. And basically in the math world, what the constraints come down to are equations, or like I said, if we have up to a certain amount, like we have up to $100 to spend, we might have inequalities as well. So equations and inequalities. So that gives us a math model. Okay. And so we have some rules with this stuff. And some of these rules are, what are we going to do when we have a word problem? First of all, we're going to read it, okay? And it's more than just reading it. So you haven't been trained very well, I don't think, throughout your life. I mean, so really probably 2 to 3 times we need to read that thing. But the reality is it could be more than that. We need to read it until you understand it. So we need to read it to understanding. Okay, we need to visualize, see what's going on. Sometimes uh, great way to visualize, like if I got a rectangle or something like that, we could draw a picture. We could draw a picture and kind of see what do we have? What do we want to have? What do we know? What are we trying to find out? And if I could draw a picture to kind of see it, like if I have a rectangle, I'm going to draw a rectangle. And then after we understand what the problem is proposing, we're going to devise a plan. We're going to devise a plan. And then third thing we're going to do once we get that plan, we're going to label our variables, which we call the factors. Okay, but only label what we don't know, but what we do want to know. Okay, and then we're going to come up after we got our variables or unknowns, things we're trying to find out. We're going to come up with the equations and inequalities based on the constraints of the problems. And then what are we going to do? After we got those, then we're going to solve it. Okay. We're going to solve, and then, of course, we always need to label. So if the length is in feet, then we need, if L is in feet, then if we get a solution of 5 feet, we need to have that labeled. And then, a lot of people just quit at this point. But then the last thing we need to do, and this is important, is we need to check it, and not only check it check it out in your equations and inequalities, but you might have solved an equation perfectly to get x equals 5, but it may not make any sense. So for example, if you get the length is -4 feet, and that may not be possible, right? Because length has to be positive. So we always want to go back to the original. We want to check it in the original problem. So go back up to the top and reread it, and with your answer in hand, and see if that makes sense. Now, what if this doesn't work? What if your plan doesn't work? Well, pretty simple deal. So if the plan doesn't work, you know, then we're going to go back and we're going to devise a new plan. Okay. So if what you did didn't work, we're going to devise a new plan. All right. So anyway, that's kind of the concept of what you've been doing your whole life. So let's, oh my gosh, I just logged out, I think. Let's see. No, I didn't. I just got out of the, y'all look like you're still there. I just got out of my black whiteboard. All right. So that's not, I hit the button right next to the clear screen. My bad. All right. So let's do a few. Let's talk about a couple of things first. Some things that we might need to do, some definitions. So DEF definition. We talk about proportionality. So Y is directly proportional to X. Directly proportional to X, if and only if. Now remember definitions, if definitions go both ways. So IFF means if and only if. Y equals some constant K times X. So I could have just wrote KX, but you know, I could put a raised dot there too. So Y equals some constant times X, where K is called the constant of proportionality. Constant of proportionality. All right, that's what K is called there. Now let's think about that. So an example is, you know, if I have Y equals 2X, something like that. Well, what would that look like? Well, it's a graph that would be a line, right? In this case, I have a slope of 2, so it rises faster than it runs. But where does it go through? The graph of a directly proportional, that's, by the way, I usually underline what I'm defining. The graph is a line through the origin. So if we have a line through the origin, we're going to have direct proportionality. Now, another way to think about this is we might have, you know, the two variables y divided by x if I equals a constant. So a proportion is a statement that two ratios are equal. A ratio would be a fraction, right? And of course, K, we could make that a fraction by putting it over 1. Anyway, so the cross products are equal, etc. All right, so we have that. Now let's go to something else here. See if I can utilize my eraser function. All right, so what if I have, so I got directly proportional, what if I have inversely proportional? Inversely proportional, okay? So y is inversely proportional to x if and only if y equals k divided by x. So inverse, think of what's the inverse of 2? Well, there's a couple different inverses of 2. The inverse of 2, you know, a lot of people think, well, -2 is the inverse. That's the additive inverse. But the multiplicative inverse of 2 is 1/2. The multiplicative inverse of 2/3 is 3/2. It's 1 over x, right? So the multiplicative inverse of x is 1 over x. And that's what we have here. This is really like y equals k times 1 over x, right? So 1 over x is the inverse. So these would be called inversely proportional. Now the other way we could say that is if I multiplied both sides by x, x times y is a constant. So the product of the two variables would equal a constant, right? Now we don't have this stuff, constant proportionality. We don't have all that, right? But anyway, that'd be inversely proportional. And then we have one more. I'm going to clear the screen, make it easier on your eyes here. But now we can do another definition. X and Y, that's my and, X and Y are jointly proportional if and only if we have something like Z equals K times X times Y, okay? So let's look at an example of this. So we can say Y is jointly proportional. So I'm going to abbreviate jointly proportional to X and Z if and only if what? Y equals some constant times X times Z. Or we could just write KXZ, right? So we have that. Now let's look at another, just one more example, and then we'll get on to actually solving some of these things. So one more example. Y is directly proportional to X and inversely proportional to Z if and only if what? All right, so this is an example. So Y is directly proportional to X, so some constant times X, but inversely proportional to Z. So it'd be over Z. So Y equals KX over Z. So this basically the reason that we're going over some of these things is we may need to know that to come up with how to solve a problem with our constraints. We may need to come up with some of these equations. All right. Okay. And once again, not really into calculus stuff yet. The beginnings of calculus start in section 4, just so you know. 4 is really awkward to read, so I highly recommend if you're looking ahead, which you're going to be for Friday, because that's Thursday's always a work day, right? So we're going to get section 1.3 done and then look ahead. So the evens for section 1.3 will be due Friday at class time, and then section 1.4, make sure you read section 1.4 and 1.5 together, because 1.4 is a specific and awkward version of section 1.5. So we're going to kind of do those together too. But anyway, before we get there, we're not there yet. We got to go back and let's just do some of these. Let's look at the evens that I told you to look at. So with this, I gotta come up with, I gotta figure out what the problem says here. So I gotta bring up my book. I don't have a book in my, I do have a book, but it's not with me. So if I go under course content and then look at the book, I should be able to bring up section 1.3 from the book. Anyway, we're going to do number 3. We've got a pendulum is what we've got. Let me get down to the problems here. So if you actually on page, I don't even know what page it is. Let's see. 27, it looks like, page 27 of the book. But the period, the time for one complete oscillation of a pendulum is directly proportional to the square root of the length of the pendulum. All right, well, that's a mouthful there, right? And the pendulum has length 8 feet. If it has 8 feet on the length, it's going to have a period of 2 seconds. So it says find a math model expressing the period of a pendulum as a function of its length, and then find the period of a pendulum of length 2 feet. All right, so first of all, we have factors and constraints, right? So the factors, what factors are like labeling your variables. What don't you know that you want to know? Well, what's the question? It says, find the math model expressing the period of the pendulum as a function of its length. So what are we gonna, trying to go back to my notes here. So let's, first of all, I'm gonna draw a picture. So I've got a pendulum. The pendulum is like, it's like a grandfather clock, right? So we got that tick tock, back and forth, right? So what happens is, you know, we've got something like this, where I'm going to change my colors here, but the period is over and then back. That would be the period P. So the period, I'm going to call that period P, and that's going to be in seconds. So here, drawing a picture might help. And then of course, what's the length? Well, the length of the pendulum is going to be right here. It's going to be this distance right here, right? So that'd be the length of the pendulum. Of course, that's the same as the length over here when it gets here too, when it goes back and forth. Okay, so all the way over, all the way back is the period. And, you know, I guess it wants P as a function of L. It's going back. What did it say? Now I'm going to go back to the problem. So one complete oscillation is just the back and forth. So trying to figure out what the problem is saying. And we said the period, which is P, so we're going to let P be the period in seconds. So this is, now I kind of labeled it on my picture, right? So I'm kind of already did this. And then L is going to be the length, and it looks like it's in inches, right? I think it was inches. No, feet, sorry. It was in feet. All right, so those are factors, and then we need to come up with constraints. Okay, well, in general, it says we want to find a math model expressing the period as a function of its length, but it says that the period is directly proportional to the square root of the length. So the period is directly proportional, so K times the square root of the length, K times the square root of L. So that was given by the language that the period of the pendulum is directly proportional to the square root of the length. So P equals K times the square root of L. So that's one equation that we have. And then, so that is the mathematical model expressing the period of the pendulum as a function of its length. So this is really part A here. That's the answer to that. And then what it says is find the period of a pendulum that has a length of 2 feet. Well, we want to, if L equals 2 feet, what's P equal? So that's the question. So we're trying to find P here. So, but what it did say, really, before we find P, you know, P would equal K times the square root of 2, right? But what we need to do is we need to find K before we do that. So we need to find K. And how do we do that? It gave an example that when a pendulum of length 8 feet, so if the length is 8 feet, then the period is 2 seconds. So it gave that as a specific example. So what we can do is plug that in up here and then find K. So the period is 2 seconds, so 2 equals K times the square root of 8. Okay, and then we need to solve that for K. So that implies that K equals 2 over the square root of 8. Well, what's the square root of 8? Square root of 8 is square root of 4 times the square root of 2, or square root of 4 times 2, which you can separate the square roots. So that's 2 over 2 root 2, right? And then I can cancel those 2's to 1. So basically, I'm going to come up with that K equals, running out of room on my screen here, 1 over the square root of 2. So that's K, which I could plug in right there. If you don't like that square root in the denominator, multiply top and bottom by the square root of 2, and we could say it's the square root of 2 over 2. Either way is fine for what K is. All right. So that's K. So then we have a new one, a new and improved equation, right? So we have, instead of P equals K times the square root of L, we have P equals square root of 2 over 2 times the square root of L, or what I like, if I just put 1 over the square root of 2, if I use that version of it, times the square root of L, this really becomes P equals the square root of L over 2 is an easier way to write that. So now I have a new improved equation, and then what I'm going to do is use this to solve part B. Part B said, find the period of a pendulum of length 2 feet. So this is part A. This is the final answer for part A, right? And of course the period would be in seconds. But anyway, if the length is 2 feet, then the period is going to equal the square root of 2 over 2, which is the square root of 1, which is 1. And then of course period is in seconds. So 1 second. And then we'll go back and check it in the original, make sure that makes sense. And should be good to go on that. So anyway, this is your answer for part A, because we actually had more information that it gave us specific where we could find out what K is. So P is square root of L over 2 seconds. And then for the one that they're asking, of course, the answer is 1 second. Now this is an odd, so answers in the back of the book. We can double check that. Got all the answers somewhere in the blackboard there too for the odds. Any questions on that? Ask now or forever hold your peace. So, all right. Another one I asked you to look at was number 11. Main reason I wanted you to look at it is because you might have said, oh my gosh, I have no idea what I'm doing here, which is all right. So let's look at it together. Okay. So number 11. Be nice, like if we're in class, I'd make you read this stuff, but everybody's on mute. We got surface area of a sphere. Well, what's the first thing I'm going to do? I'm going to draw a sphere, draw a picture so I can visualize what's going on here. Okay. Surface area of a sphere is a function of its radius. Okay. Well, it's talking about the radius. Since I got different color clicky pen, I can do that. There's my radius. And we got surface area. Does anybody know what the surface area of a sphere is? Surface area of a sphere is, isn't that 4 pi r squared? And it'd be square units, whatever the units are. In this case, it's centimeters. It's r centimeters. The radius was in centimeters, so this would be in centimeters squared because of surface area. Now, some of you might wonder where this equation came from. You learned it in geometry, but geometry got it from calculus. So we're going to find this out later on. If you take enough calculus. All right, anyway, so we've got surface area. They're calling that A of R. A of R. It is a function surface area instead of f of x, it's surface area in terms of the radius. And this equals 4 pi r squared. So we just got that here. So that was actually given. Now, then it says, suppose a balloon, which apparently they're assuming that's a perfect sphere. It's not going to look like a hot air balloon. Maintains its shape of a sphere as it's being inflated, so the radius is changing at a constant rate of 3 centimeters per second. So that means it's getting a little bit bigger, right? And we already talked about 2.54 centimeters in an inch, so it's getting bigger at a little bit over an inch per second as you blow it up. And then it says, if f of t centimeters is the radius of the balloon after t seconds, so do the following. A, compute. So we've got f of t is the radius after t seconds. And then it wants us to compute A composed with f evaluated at t. So this is the first one. And interpret the result, and then find the surface area of the balloon. This is A, and then B, we want to find the surface area of the balloon after 4 seconds. All right, so let's go back and do this. All right, so everybody understands the concept of the problem, hopefully. The balloon is getting bigger, okay, as it gets blown up, right? So it's growing, getting bigger, right? All right, and then of course this radius would be a bigger radius, right? All right, so that's what's happening. So A of f of t. So let's go back. So we know, what do we know? We know the radius increases at 3 centimeters per second. Okay, and f of t is the radius. Instead of calling it r, we could say radius, but anyway, at t seconds. So the question would be, how do we come up with what f of t is? We need to figure that out, right? So let me clear this annotation, give a little room to work here. So I'm just going to do a little t chart, t f of t. All right. Well, if I haven't blown up the balloon at all, so at time t equals 0, my radius would be 0, right? So the f of t is r centimeters, right? So I wouldn't have a balloon. But if I just go 1 second, it's increasing at a rate of 3 centimeters per second. So that would be 3. If I blow it up for another second, what would my radius be? It's increasing at a rate of 3 centimeters per second. So that would be 6, right? Well, if you notice, and I could come over here and draw a little graph, but 0, 0 is on my graph, over 1 up 3 is on my graph, over 2 up 6 is on my graph. What's that? And of course you all have, or we have all these fractional seconds we could do too. But what kind of relationship is that? This is a linear relationship. The graph is going to be a line. And basically if I say, well, what if I have blown up that balloon for t seconds? I'm going to end up being 3t feet. To get from here to here every time is, I can do that by multiplying by 3. So since I'm increasing by 3 centimeters each second and I started at 0, f of t is actually going to equal 3t. And that's the radius after t seconds. Okay? So now what I'm going to do for part A, it says calculate A composed with F evaluated at t. That's actually A evaluated at f of t, composition of functions, right? Which is A evaluated at 3t. And of course, what was our equation that was given? The surface area for radius r is 4 pi r squared. And here what we're doing, A of anything is 4 pi times that anything quantity squared. What's my anything? Is 3t. So basically, this is going to equal 4 pi times 3t quantity squared, right? And when I quantity square that, it's going to be 4 pi times 9t squared, which is 36 pi, always keep the constants together, t squared. And that's going to be the surface area after t seconds. So what would the label be? The label on this would be centimeters squared. Hopefully you can see that. So A composed with f of t is 36 pi t squared centimeters squared. Okay. So what's the interpretation? I'm not going to write this out in words, but at t seconds, the surface area is going to be 36 pi t squared square centimeters. Okay, so that's part A. So we're done with part A. So check that one off. And then now I'm going to go back, clear this off, and then part B said, hey, now we want to find the surface area when t equals 4 seconds. The surface area when t equals 4 seconds. A couple of different ways to do this. T equals 4 seconds. First of all, we could find the radius. But instead of doing it piece by piece, we already have our equation that this is a of 3t is going to be a of 12, right? So if we found, like, say, hey, what is the radius? Radius is going to be f of t, which is 3t, but t is 4. So this is, radius is going to be 12. So a of r is a of 12. So that's fine. This is finding the radius first, which is going to be, you got to be careful here which equation you're using. A of r was what? This was 4 pi r squared. So we got to be a little bit careful which equation we're using. So 4 pi times 12 squared, of course, 12 times 12, a dozen is 144. So this would be 4 pi times 144. And of course, what's 4 times 144? Well, I don't multiply by 4, I just double it twice. So 288, 576. So this is 576 pi. And then what's surface area? Square centimeters. This is one way to do it, but that's, we've already done the hard work, right? Where we had a of a composed with f evaluated at t. Sorry, I got some commotion in the background here. A composed with f is was 36 pi t squared square centimeters, right? So this is just going to be, hey, my time is 4 seconds. So a composed with f of 4 is just 36 times pi times 4 squared. Notice this is the different equation that I came up with for the composition. Instead of doing it step by step up here where we had to figure out r separately, I've already done that in part A. So utilizing part A, we had this equation for us. Anyway, so this is 36 pi times 16. And of course, 36 times 16, I'll let you verify, is 576 pi square centimeters. Okay. Any questions on that? Hopefully not. Hopefully it's perfectly clear. Let's see how much time we got. Time for 1 or 2 more. So we could go on to maybe number 13. And by the way, it's going to be important that you do some of these odds on your own too, to make sure that when you're getting them, that you're matching the answers. Okay. So let's move on to 13. Okay. So anyway, 13A, let's go back and see what that says. A rectangular field is enclosed with 240 meters of fence. Find a mathematical model expressing the area of the field as a function of its length. All right, well, this one is, that's part A, math model. If I draw a picture, I'm going to draw a picture. Now, if I had a river up here, I wouldn't have any length there, but this is length, this is length, this is width, this is width. So we know what a rectangle looks like, right? And we said that there's 240 meters of fence. Well, the perimeter is 240 meters. Okay, well, what's perimeter? It's length plus width plus length plus width, or it's 2L plus 2W. So we have 2L plus 2W is 240 meters. And of course, what's L? So the factors, if we're labeling our variables, L is the length in meters, and W is the width in meters. Now, if we can replace and just get down to one variable, great. We could do that. Anyway, by the way, what would this reduce to? And this is constraints over here. Constraints are limitations on what can be accomplished, or equations. Anyway, I could divide everything by 2, both sides by 2, and I got L plus W equals 240. So with that being said, I could also say instead of L, I could solve this for, or L and W, I could put L and then something in terms of L. So if I solve this for W, I would get W equals 240 minus, not 240. I got to take half of that, don't I? So that was 120. So anyway, W equals 120 minus L, right? So instead of W, I could say 120 minus L is going to be the width over here as well. So I could say 120 minus L. All right, so hopefully that makes sense there. And then what did it ask us to do? Find a mathematical model finding the area in terms of its, what did it ask? Length, hopefully, because that's what I solved for. If it said in terms of the width, I'd want to solve this for L and replace it up there. But anyway, what's area? Area is length times width, right? So in this case, what's the width? Area in terms of L. So instead of f of x, we could call it a of L. That's not a times L, it's a of L. It's a function. It's going to be L times 120 minus L. And then, of course, that's going to be square meters. All right. So this is the mathematical model of the area in terms of the length. And then what else does it say? What is the domain of your function? Well, it wants to, so part B, it says, what's the domain here? So let me clear this off. So we had A of L is L times 120 minus L. And the domain of A, the domain of your function, what could L be? L could be an element. Well, certainly, could it equal 0? First of all, it's got to be positive, right? So basically our picture, we got L and 120 minus L. If L is 0, I don't have a rectangle. So it has to be greater than 0. So it has to be some kind of positive number. So I'm not going to include 0. And then how big could I go? Well, the biggest I could go, if I plug in like 60 or things like that, I'm fine. Anything up to 120, if I plug in 120, I get 0 for this part. And of course, I can't let it equal 0 because if the width equaled 0, I wouldn't have a rectangle either. So this is the domain. So the other way we could say this is L would be an element of 0 to 120, not including the endpoints, or we could say 0 meters is strictly less than the length, which is strictly less than 120 meters. Any of these are correct ways to say what the domain of this function is. And then the last thing it's asking, by plotting on your graphics calculator. So this is a good point here. I'm about done, and then I'll finish this up, and it's on recording too, but it won't take me long here. We're not going to use graphing calculators. So what can we do? And we're trying to estimate to the nearest meter the dimensions of the largest rectangular field. Well, so how are we going to do that without a graphing calculator? What we're going to do is we're going to try and graph this thing. So what is this? I'm going to change colors here. This is equivalent to 120L minus L squared. Do we know what that looks like? So it's like y equals that. Well, that's a parabola that opens upside down. So I could say it's minus L squared plus 120L plus 0, right? But anyway, what this is a parabola, upside down parabola. And once again, if I've got L and then A of L here. Now remember, we could go between 0, not including 0, and what was A of L? A of L was L times 120 minus L, or like we said, 120L minus L squared. Upside down parabola, but if I go out to 120, I'm going to be at 0. If I go at 0, I'm going to be at 0, and we could come up with, hey, what's the vertex? The vertex occurs at negative b over 2a, and negative b, the opposite of b, would be minus 120 over 2a would be minus 2. That occurs at 60. And if I plug in 60, what is A of 60? Well, it's 60 times 60, or 60 squared, which is 3,600. Okay, so 3,600, we'll just put a vertical scale on there. When I'm right in the middle at 60, I'm at 3,600. It opens downward from there, and it's going to be symmetric through the, basically the x equals 60 line. But anyway, it's saying what is the max height? The max height is right here at 3,600 meters. So anyway, so that's the largest area. And when does that happen? When we have a 60 by 60. So 60 by 60, 60 meter by 60 meter rectangular fence, we're going to have the largest area, which actually makes it a square. So that's all for today. Try that last odd on your own, and a couple other odds, but the evens are going to be due, and we'll go from there. All right, thanks.